Hello there. Welcome to our today's science lesson. The topic for the day being physical and chemical changes. An overview of our previous lesson, we looked at what are the aspects one should look at to classify any reaction or any process or any substance that is undergoing a change as either a chemical change or a physical change the substance will have undergone. And in that case, we looked at what are the points associated with the chemical change and what are the points associated with the physical change. We saw that some of the changes associated with the chemical changes are like when you look at the product in relation to the reagent, the product will have a different identity from the reagents. You can look at the change in mass, where you will find that the product will have a different mass in comparison to the reagents. Looking at reversibility of the reaction, we saw that in a chemical change, whatever will have taken place as a change cannot be easily reversed, that is by physical means. It can only be done maybe by chemical means, but not by physical means. Just to mention a few. And on the other hand, when you look at a physical change, you discover that looking at the reagents and the products, the difference is not so much. The reagents and the products are the same. They may change maybe just in terms of the states. Like for example, if you have water, which was in ice form, it has now melted, it is in liquid form, that's just a change in state. But looking at what has happened, being a physical change, you can easily reverse back the liquid water to solid water, which is ice. So this shows that in a physical change, the product and the reagents are not different. Looking at the mass, change in mass, you will find that most of the physical changes, there is no change in mass. Looking at water, the mass in a liquid state will be the same mass in a gas state so long as no single particle will have been lost. If everything is collected, or in ice form, there will still be the same mass so long as you make sure that no single part of the substance undergoing the change has been lost. Looking at identity, it is still that water, it is still that substance. Look at a wax, that's a candle, that's wax. You melt it, it will go in a liquid state. You leave it to cool, it goes back. That is a physical change, and so many other of that kind. In our today's lesson, I want us to look at there's so many changes, there's so many reactions we see around our daily lives. There's so many things we see around our daily lives, and try to classify them as either physical or chemical changes. You may be surprised. Some of the changes we are going to mention may look too complicated when it's just a simple thing, or look so simple when it's a bit complicated because it is either a chemical change or a physical change. Now, I will try to look at mention some of the processes that we always see around and try to classify them just as an addition to what we had already done in the previous lesson of classifying so many changes or processes or encounters we encounter in our daily lives as chemical and physical changes. Maybe number one, let's look at when you light a matchstick. You have a matchbox, you get out a matchstick, and you try to ignite the matchstick. You will find it lighting. What exactly has taken place? When you have that matchbox, which has a surface, it is usually rough, so that it creates what we call friction. So this matchbox, which has a rough surface that has been smeared by a particular substance, then you have a matchstick which has a head. So you will strike the head on the surface of this matchbox at the rough point. What you will see next will be the matchstick will have lit. Now this light or this flame is coming from this part lighting up, getting burned. So when it is getting burned, what change are we seeing? What change are we seeing? The change is, since this is a compound, it is a compound, most of them are chlorates of different materials, but commonly chlorates. When you burn this chloride in the presence of oxygen, remember air is a mixture, and part of that mixture we have oxygen in it. So when they are burning in oxygen, you will find that the compound that will be formed will be totally different from the compound that was originally in the head of the matchstick. After the head has burned, put off the flame and look at it again. Do they look alike? The answer is no, they don't look alike. If you try to break off the head and take a matchstick that you haven't burned, then try to compare if each one of if the two of them are of the same mass, the answer will be they will not be of the same mass. So you can see the appearance is different, the mass is different, and now even to be exact, the chemical composition is different, because after burning you have formed an oxide of that particular compound, but before burning it was a different compound. Then this one essentially tells us that when you burn a matchstick after lighting on a matchbox, the change that the matchstick will have undergone is a chemical change, not a physical change. And that's why you can never reuse a matchstick that you have already used, because it has undergone a chemical change, not unless it is reversed, and it can't be reversed by physical change or physical means, but it can only be done by chemical means, which is not that easy. Now let's look at another one that is so common in our lives. You have heard of maybe a bomb being used somewhere in war, or maybe during extraction of some materials like rocks, stones. You may use small bombs put in the graves of those maybe big rocks. Then as it blasts, at least you will have an easier time of getting the stones now that they will have been fragmented. Now the question is, what has happened? Looking at that particular bomb, what has actually happened? When you look at a bomb, this is a chemical. Whatever is found in that casing that you call a bomb, whether a grenade or whatever, so long as is an explosive, whatever is found inside is a chemical. Now what happens is the chemical undergoes a reaction, a sequential reaction, producing a lot of energy. And since that energy cannot be held in a closed state the way it was originally, since it is a lot of energy, it will have to go out. As it goes out, that's how it is seen to be an explosion. It's just an issue of having a lot of energy. The energy can be in terms of the sound energy, the heat energy, light energy, and even some radiations that are produced. Like if you look at these heavy bombs like nuclear bomb, atomic bomb, those are bombs that in addition to the energies I've mentioned, you will have also some radiations coming out of it which are very dangerous. We have gamma rays and X-rays, very penetrative, cool but very penetrative, and can cause so much harm like mutation in animals. Now, if you look at the explosion, how it has happened, you go back and now try to look at the materials that were inside the casing. Do you think they will still be looking alike? The answer is no. They will not. Maybe for the case of something like a nuclear bomb, I may not go into it so much because that is a topic of another day when we shall be looking at things like radioactive decay. Maybe at that point we may be able to understand that aspect very well. But look at a bomb like trinitrotoluene, TNT. So maybe you must have heard of it. TNT, trinitrotoluene. This is a bomb that is made from a reaction between toluene and nitric or nitrogen based. They can even use fertilizers. We have nitric acid, which has a nitrate in it. So essentially, you are just using toluene all of these are hydrogens. Then you react with this such that you will have your nitrate here, another one there, and another one here. So having formed this, here you have a bomb. This is a very unstable compound that under any simple, just small uncomfortability of energy, then it will explode. After it has exploded, it doesn't remain the way it is. You will have to form other compounds, including carbon dioxide and the kind. Now, looking at that, do we have such a compound like carbon dioxide here or carbon dioxide? Carbon dioxide and carbon dioxide are one and the same. The answer is no. So what has happened? There's a change in identity of the products in relation to reagents. Then which kind of change could this be? The answer is only one. Chemical change. Because the product and the reagents are different. Maybe let's look at another one that is a little bit very common and see. Chopping of wood. Chopping of wood. You have a panga, knife, an axe, whatever material you are using to chop wood. Or even in industries, where paper industries, where we have wood being chopped into small chips using machines. Still the same, you are chopping wood. Now, one can look at it that wood that was a big log is now in very small chips form. So many will always want to categorize such as a chemical change because you cannot be able to reverse that small chips. Make them combine to go back there to the original form, which was a big log of that particular wood. But in reality, that change is not a chemical change. That change is a physical change. What you have only done is you have subdivided the big piece into smaller pieces. If you can use something like glue, you can still reconstruct that piece of wood using those chips, glue them together, and you will form that big log of wood. Though originally you had not used that glue, and now you are using glue, but still that cannot qualify you to say, since you cannot use the natural way of gluing the chips together to form the log, that's a chemical change. No, that is a physical change. So chopping of wood into small pieces is not a chemical change, but it is a physical change. Another common aspect that one can look at and kind of get confused is when you have an aspect to do with the cooking. You are cooking any kind of food. Imagine of that egg. You are frying it, or whichever way you are cooking it. Maybe boiling it, you break it, then you fry it, still cooking. At the end of the process of cooking that egg, or whichever type of food, does that food look like it was previously? The answer is no, it doesn't. And in fact, that's why it is always encouraged that cook your food and thoroughly cook the food before you eat. What essentially you are doing is you are using heat energy by boiling the food to break the chemical components in that particular food so that your body can easily absorb the nutrients from that particular food material. So what you have done is you have changed the chemical composition of the food material. You will have changed the chemical composition of the food material. But this does not apply to all food materials. So that's why I'm particular an egg, because I'm also going to mention a particular type of food material that even if you will have boiled, still there's no change that will have taken place. So when you are boiling an egg, you will find that before you will have the yolk, the yellow part, you have the albumen, the white part. But after cooking, you find that all the two have mixed and they almost look the same. If you didn't stir, then the yolk will be on its own, the albumen will be on its own, but physically if you look at it, try to feel it, it will be totally different. What has happened is the food composition in the albumen or in the yolk will have reacted with the air, that's one. Remember you also used oil. So with the oil, that's two. And probably you also added there salt, common table salt, that is three. And maybe any other ingredient that you added in. So all these things you have added are chemical compounds. Being chemical compounds, and an egg is a chemical. All foods are chemicals, but of different types. Chemicals, but of different types. That's why you can call these ones carbohydrates, call these ones vitamins or proteins, and so on. So when these chemicals combine, they will obviously, under the effect of heat, give rise to a different product. So that makes frying or cooking an egg a chemical change. The product and the original are totally different. So that makes it to be a chemical change. But let's look at it in terms of cooking, but a different type of food. Look at something like rice. A rice grain will have different sizes. If you look at that rice grain, rice is in the category of carbohydrates. This is a food material that is generally used in the production of energy. So this rice grain, when you put it in a sufuria, you are boiling it. It is in any container you are using to boil the rice. So you have heat energy so that this one can boil. After boiling, if you feel the rice, it will be soft. But originally it was hard. What has happened? The only thing that you have done with this heat energy, assuming that you haven't added there any other material. You haven't added there any other material. It was just an issue of boiling. Then you are only softening the rice grain. But the chemical composition of the rice grain will remain the same, and that is starch. That is the chemical composition of the rice grain. Though, even an egg, the argument will be the egg will still maintain the protein chemical composition. But remember, that protein, it is a different chemical component compared to starch. It is active. And also, in addition, in the egg, we have so many other minerals that On heating during frying, it will react with the air and with itself to form other different substances, and that's why the egg usually changes from the way it was to the final bit after cooking. But look at rice. Rice only does one thing, softening. So you only soften the starch, which was in hard form, now it is in soft form, so that when it goes into your body, it can easily be digested and absorption takes place. So for boiling of starch, that is a physical change. But for frying of an egg, that is a chemical change. Now let's look at another thing, very common indeed. I may have also mentioned earlier, but I'm still mentioning it right now. Rusting. Rust. If you look at rust, rust occurs on a metal by the name iron. So iron undergoes rusting. Iron undergoes rusting. Now, we need first of all to understand what is rust. Before now, we essentially categorize it under physical or chemical changes. So rust, having known that it comes from a metal by the name iron, you need to realize that for rust to take place, we need conditions favorable for rusting, and that is presence of oxygen gas and presence of water. So for you to form rust, you need these three things, because even if you have the conditions and you don't have the surface or the material onto which rust will take place, then rusting will not take place. So we require these three things: iron metal, oxygen, and water. Now, these are the original substances we are talking about. Iron as iron, oxygen as originally oxygen, and water as water. But on combining these three, you come up with the rust. And what is rust? Rust is hydrated iron 3 oxide. Hydrated iron 3 oxide. Let's relate the name to the conditions necessary or to the substances supposed to be present for rusting to take place. Hydrated. Hydrated means presence of water. So this one we can relate to water. It is water that is creating the hydration of rust. Then we have what is undergoing rust. So we can relate it to iron metal, the iron itself. Then 3 we shall relate it to color. I will talk about it. So we have 3, we are relating it to color because we know rust to be of a particular color. And oxide, we relate the oxide to oxygen. We are relating oxide to oxygen. So what are we seeing? We are seeing 3 things coming together to form one thing by the name hydrated iron 3 oxide, which is rust. Now, when I talk about color here, iron 3, iron has 3 oxidation numbers. We have what we call iron 2 and iron 3 ions. So these are the 2 stable ions of iron. This ion is normally green in color, and this one is brown in color. Now looking at rust is brown in color. Rust is brown in color, showing that the rust formed does not utilize iron 2, but it utilizes iron 3, and that's why it is a hydrated iron 3 oxide. Now, if you have ever encountered rust, Can you reverse rust back to oxygen, water, and iron metal? The answer is no, you cannot. You can only do it if the materials that have undergone rust are collected, taken back to an industry where chemical means will be used so that you revert back to iron metal. Something that will be well understood when we are talking about extraction of metals. And extraction of metals, you will talk about extraction of iron, extraction of zinc, extraction of aluminum, all of those metals. Mainly these most common metals. And in iron, we have what we have as a smelting, furnace, all those processes, but they are chemical. They are not physical. So what does it tell us? Rusting is a chemical change. Rusting is a chemical change. Because reversing it back, you require chemical processes in the industry. But physically, it cannot be done, making us take rust as a chemical change. So the formula of this rust therefore becomes, is good because you remember in our previous topics we talked about formulas. So the formula of rust becomes ion. Remember this ion, capital F, small e, oxide. Now with this oxidation, remember also in the previous topics we talked about combining powers. Combining powers. So whenever they are forming a compound, you have to look at combining powers. So the combining power of ion, we are picking on that of 3, not of 2. So the combining power of ion is 3. And we say that when using combining powers, you interchange. So the combining power of ion goes to oxygen, which is 3. And the combining power of oxygen is 2, which goes to ion. But it is hydrated. So hydrated means we add there water. Now I will use here X to show that this rust, depending on where it is, it will have varying amount of water in it. If you immerse an iron piece in water for some time, maybe days, then you have another one just in air, they will all form that brown material. But if you go look at that rust, one will look to be more wet than the other. So being more wet, it means X will be a bigger figure, and being dry means X will be a smaller figure. So there is a variation in the amount of water. But all in all, we shall be having water to qualify it to be hydrated iron 3 oxide, which is called rust, a chemical change. Reason, the product is totally different from reagents by identity. Product is different from reagents by mass. Product is different from reagents because you can also look at the combination, and also it cannot be reversed physically. Now, let's also look at some of the processes we may be hearing of, because probably you have never seen it being done, and it also causes confusion. And one of it is like when you are hearing of metals like steel. Steel is not a pure substance. But how do we form steel? And if you have formed steel and it's not a pure substance, is the process of forming steel a chemical change or a physical change? We shall answer that question by looking at how we combine to do that. Now, In steel, we have iron. In steel, we have brass. Steel, we have iron. Steel, we have brass. Why do we go for these two? Brass is rust resistant. You cannot make what we have just talked about here in terms of forming rust. But iron, you can see it forms rust. But why use iron? Iron is a strong metal. Iron is a strong metal. So, in forming steel is a combination of a rust-resistant metal and a strong metal. Because remember, in most cases, we want strong things that are water-resistant. Look at most of the implements or items that are used in the kitchen. Kitchen is always associated with water. You are cooking, you are using water. Cutting something, water is around. Must have washed that, tomato, and all that. Look at some of the machines we use. They are commonly associated with water. Some of them. Or at least, even if it is not associated with water, but at one time, accidentally, water can come by. It has to be able to resist it because rust interferes with the strength and operation of a particular metal. Look at the ball bearings in a machine that makes parts to move freely, like free wheels. They have ball bearings in them. Imagine if that ball bearing had to rust. Will the machine move? The answer is no. So how do you achieve that? You achieve that by mixing a strong metal and a water-resistant metal, and that is brass and iron. Brass, when it breaks without warning. It is brittle, but iron can easily bend. So this will explain to you why when you have a steel metal, if you bend it, if you apply a lot of energy, force on it, it can slightly bend because of the iron in it. But if you force it so strongly, then it breaks without warning, brittly. That is because of brass. But remember, it does not rust. And also, it is strong. It is because of brass and iron. But is the formation of steel a chemical change or a physical change? It is a physical change. Why a physical change? Is because it is just a process of physically heat iron to melt, physically heat brass to melt, then mix. Pour one to the other, stir, cool. And you cool it in a shaped container such that it can now take whatever shape of the item you want. So that qualifies it to be a physical means. If you want to separate, so long as you have a furnace, a point where you can heat that steel and it melts. Once it melts, since these two metals, iron and brass, have different boiling points, different melting points, different densities, these are physical properties. Because of those physical properties, you can easily apply the physical differences, like now densities, to separate the two, which will be a physical means. So even if you have applied heat energy, but the change will be a physical change. This also applies to formation of bronze. Bronze is a metal that is commonly associated with the winning, where number 1 or position 1 is given gold, second silver, and the third bronze. Bronze is just a mixture of copper. Remember, copper is commonly used in wiring. And if you take copper, put in water, it cannot rust. So that is one of the aspects that was taken from copper. Another aspect that was taken from copper to be used in the formation of bronze is the aspect of the color. If you look at the color of bronze and you look at the color of copper, they almost look alike. So copper is used, and just like in the formation of steel, formation of bronze is a physical change, since you just melt the two metals, mix the two, and you form bronze. So that is a point where in some way one can easily imagine the formation of the alloys. Those are alloys. The formation of the alloys is a chemical change, when indeed is a physical change. Maybe relating it to our common or anything common to us is like when you have water and accidentally you had maybe ethanol and you mix the two. You have poured ethanol into water or water into ethanol. That's a mixture. Can you be able to separate the two? The answer is yes. Just use distillation, which is heat, and using physical differences of boiling points, you will separate the two by collecting ethanol first at around 78 degrees centigrade and water at around 100 degrees centigrade. But remember, it must be at sea level, because the boiling points vary from point to point depending on how high or how low is it from the sea level. If it goes high, then the boiling and melting temperatures go low, and when it is low, the boiling and melting temperatures go high because of the high pressure. So you have to remember always to mention the word sea level whenever you are talking about melting or boiling point of a particular substance. Now, another issue is about, these are common things we always encounter. You are making an object from a molten metal. Take an example if this was a piece of metal. Was it found from its natural setting this way? Assuming it is iron, now that you have talked about iron. The answer is no. It wasn't found this way. It was found as an oxide, which was taken to an industry, then a lot of process was done until you got iron. But now, I want us just to look at the last point in that industry, when it is being rolled into such a shape. Is that rolling chemical or physical? It is physical. Why? Because the iron or the zinc or the aluminum, whichever the metal, was just first melted. After being melted, it was to be shaped, and in shaping you can roll it into maybe such a rod, or you can shape it into sheets, like you have heard of iron sheets, or whichever shape you want. So in that shaping, you are only working on it physically. So being that you are changing from molten to solid, a process commonly we call, for example, if you are using water, if you move from water to ice, that is freezing. So this one will just be changing from molten to solid. That is a hardening of iron. You are just hardening iron, changing from molten to solid. That is a physical means. You are only playing around with the melting temperature. You are only looking at the melting temperature, whereby you lower the temperature to below melting temperature. Once it reaches at that point, the molten will turn back to solid, because it is now out of the temperature that will make molten, the metal to melt. Instead, it is moving now from molten to the solid. That is a physical change and not a chemical change. So one can look at it to be, since I am moving from a liquid state of a very serious metal, very hot indeed, and now I'm making a very cold metal, a different shape is a chemical change? No, it is a physical change. Now, we have looked at so many examples, and that is just a tip of the iceberg of the so many things we have around us. So many things we have around us that we always question whether if they are chemical or physical changes. But I will wish now we look at it as we summarize our lesson in terms of particles. In terms of particles. It's also good you know what exactly takes place when that physical or that chemical change is taking place. And when you talk about particles, it means if it is a rod of, for example, iron, let's look at the small particles inside this rod, which are iron atoms. If it is water, let's look at the small particles, which are water molecules. If it is any other compound, let's look at that formula of the single particle, the simplest in that particular compound. So, I will be using such to represent a particle in any particular substance. Now, I will start with the iron metal being rolled or being shaped into whatever shape one may wish to. So, if you have an iron metal of this shape, these are small particles in the iron metal. So we have a rectangular shape of iron metal. These are rectangular shape of iron metal. If maybe you can cover the boundaries, that is it. We have a rectangular shape of iron metal, but it is thick. Is it possible for us to reshape this metal into a different one? So we move to this. Maybe you want to make a plate of the same. So at the end, you have this kind of shape. Let's ensure that the number is the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6. So let's maintain the number as 12. So we have maintained the number of small particles in it. But look at the shape. What have we done? We have physically changed the shape of the bar, the iron bar or whichever metal. What makes this to happen? This one has to go back to what we also learned in our previous topics, like the forces that hold the particles together. So, since the forces holding the particles together can easily be broken by high energy, that is heat energy. When you have a lot of heat energy applied to this, it will make the particles to vibrate, though in a fixed position, but at a higher level. So by vibrating, and now you start hammering, you use a heavy metal or substance to hammer this, then you can easily shape this to this. What we are showing here is the particles can easily move from one position to another. And by moving, you are only doing it in a physical way. You are moving just like where you are seated, you can easily tilt yourself to another position. You have only moved, and that is a physical process or a physical change and not a chemical change. So the same to this is a physical change, shaping a metal from one shape to another, or even the aspect we saw of molten iron moving to maybe a rod or a flat piece of that metal. Still, that will be a physical means. What you have only done is you have rearranged the small particles in that particular substance. Now, let's look at what happens to a chemical change? What happens to a chemical change? When you have an example of, let's say, sodium metal, and you burn it in air. You burn it in air, and in air our point of interest is oxygen gas. Then you will end up forming sodium oxide. You will end up forming sodium oxide. So in terms of particle, we are talking about a substance like this particle, this sodium. Then we are having oxygen. Let me use this. It usually forms two bonds between the two oxygen atoms. So we have these and these combining. What shall we have at the end? Because we have to show that the end and the start are either the same or they are different. The previous one we have seen they are the same. It's only the position that had changed. It has been shaped. You are standing at this point, you have been pushed by hammering to that particular point, but you are still the same. But let's look at this. What we are having here is now oxygen and sodium have combined, and they have combined to form that's what you have formed. So we have two sodiums coming together, and we have one oxygen. Remember, this is representing oxygen, and this one is representing sodium. So this is the product. Now look at this product in relation to the reagents. Does it look like any of the reagents? It doesn't, because even if we have a triangle here, here we have 2. Even if we have a 0 here, here we have 1. And even if they are there, they are attached, but here they are not attached to each other. So what we are already seeing is a change in identity. Look at mass. This sodium is usually 23. Oxygen 16. So a total here of 32. What do we have here? We have 16 plus 23 plus 16. Already by mass is different. In addition to identity, mass is also not accepting to be the same. Looking at even the physical appearance, you find that even the physical appearance changes. Though even in the physical changes, we have physical appearances, but here in addition, we also have physical changes. Sodium is color, oxygen is color, and sodium oxide, they are totally different. Here you cannot be able to see oxygen, but here now you are seeing oxygen. In the name of, it will have changed the color of sodium to be of sodium oxide, meaning that oxygen has taken part in changing the color of sodium, which was silvery, but this one will be a white solid. This one is silvery, but this is a white solid, meaning that oxygen has played a part in it. In addition, we also find that we achieved this using a flame. So heat energy is involved. Now, we also have mixtures. We have mixtures. What happens to when mixtures, we have maybe this in a mixed form. We have a mixture of such an arrangement. Then something happens. Take an example of something, a substance that undergoes sublimation and another one does not undergo sublimation. So if you do some heating, the substance that undergoes sublimation will go out of the mixture and leave the other one intact. So let's assume this one undergoes sublimation. So what shall we see? We shall see that at the end, you will see in the container only this one remaining. But this one will be on its own somewhere else, on a cold surface, because it has undergone sublimation, and obviously it will have to form on the cooler surface. So we shall have the two now separate. Is this a physical change or a chemical change? Since you have used physical means, just mere heating, and the two are separated, physical means heating, then it makes the change to be a physical change. So separation is just a physical means since the two have changed. But now, to confirm that, let's look at the products in relation to the reagents. Looking at the substance that has undergone sublimation, how it looks like, and this one, there is no change. That's the same. Looking at the one that does not undergo sublimation and the one that is on this side, they are also the same. So this confirms that in a physical change, there is no change in identity of the product in relation to the reagents. And lastly, let's look at water. It's a common thing. I'm sure even at home, probably you boil some water. Maybe during cooking, or maybe to take a shower, you went in for a hot shower. There's something that happened. So let's look at the particles. In a container, you have the water molecules. Remember, these water molecules are in a liquid state. These water molecules are in a liquid state. So they can easily move around, roll over each other. Remember the properties of a liquid. Particles roll over each other. That is movement. But they cannot do any other movement apart from rolling over each other. And that's why water can easily be poured out. They are rolling. Now, when you put in heat energy, which is a physical process, this is just a physical process, what you do is you make the particles to have high kinetic energy. And high kinetic energy means the particle will start vibrating much higher, much strongly than it used to be. So it will make some of the particles to now break off. You will still have those that are below, maintained in the container. But there are those that will break off. But remember, they are still water molecules. The only difference is they now have one thing, high energy. And because of that one thing, which is high energy, due to the high temperature, of course, it is due to the high temperature, they will now have a much bigger space through which they can move. They can move randomly, faster, and to all direction. Randomly, faster, and to all direction because of the high energy. But the issue here is this particle different from this? The answer is no. This is still a water molecule, and this one is still a water molecule. The only difference is this water molecule is in a liquid state, and this water molecule is in a gas state. This water molecule has less energy, and this one has high energy. Those are the only different things. But in terms of identity, the water remains water. As steam, as water, or even as ice. Even if you had ice closely packed together, remember, in a solid state, particles are usually closely packed together. So still the molecules will be that of ice, which is just water. The only difference is change in energy. So as you can see, our today's lesson, we have entirely been just looking at what exactly happens around us in terms of categorizing it into either physical or chemical changes. And you can see that we have both physical and chemical changes taking place around us. I will ask you to go on your own, try to identify on your own some of the things that take place when I mean the changes that take place when the various processes, activities, you as an individual is involved. And one of it is as you are seated there and you start probably doing an activity and you start sweating. That's a biological process. It's a biological process. You start sweating. Is it a chemical change or a physical change? Food for thought. That marks the end of our lesson today. Thank you.